Okay, so 13.1, experimental and theoretical probability. We're going to be doing a lot of writing today, so I'll try to write slow, but make sure to pay attention and be on top of it. If you don't catch something, then I'll have the notes up here afterwards, so you can always come and take a photo or copy down whatever it is you miss. Right, so in dealing with probability, we're dealing with numbers, obviously, because it's math, but we're dealing with a lot of kind of more abstract reasoning. We're reasoning about, what's the probability of my rolling a 2 and a 1 on a 6-sided die, or what's the probability of a certain baseball player hitting, a home run and for the rest of the season, or whatever. So these different percentages, and we're going to have to think about a lot of problems that are usually expressed in words. So a lot of word problems, which some people really like and some people don't really like. In terms of what the formulas you have to memorize, it's pretty sparse. So whereas with the last unit, you had to know the quadratic formula, you had to know the vertex form, you had to know negative b over 2a, stuff like that. For this unit, we won't have as much of that. So that might be a good thing. But we'll need to know what some concepts mean because they'll be used in the question. So here's one, sample space. Okay, sample space. It's just all possible outcomes we are considering. So, for instance, the easiest example, I think, or one of the easiest, is the example of a dice, so a 6-sided dice or die. All the possible outcomes you have when you roll that die there's 6 possible outcomes, 1 through 6, right? I'll get one of those numbers when I roll it. It's not like I won't get any of those numbers. It's not like the dice will somehow get, I don't know, anyway. Not like a 7 will suddenly appear on one side or whatever. It's going to be 1 through 6. So that would be my sample space, 1 through 6. Now an outcome is just a possible result in the sample space. So my sample space for rolling a single 6-sided die is 6, 1 through 6, and an outcome is just a possible result. So an outcome might be 2, or an outcome might be 4, or 5, or one of those 6 numbers. And then finally, an event single or multiple outcomes in the sample space. Okay, so an event, when I roll the single 6-sided die, might be, well, just like an outcome, I'm rolling a 2, or it might be multiple outcomes. I'm rolling, what's the probability that I roll an even number? What's the probability that I roll, when I roll 2 dice at the same time, what's the probability that the sum adds up to 10, let's say? Stuff like that. Those would be multiple outcomes in a single sample space. So you can think of it, if you were to draw it, in terms of this big rectangle being sample space. You don't have to draw this unless you think it would be helpful for just remembering kind of how these terms function. An event is part of that sample space. So the sample space is made up of all the outcomes. An event is just certain outcomes that happen. And then there's just like a single dot that's just basically one outcome. So sort of decreasing in size. Okay, so those terms under a belt, we can move on to the 2 types of probability we'll be thinking about today. So the first is theoretical probability. And this is just calculating the probability of an event prior to experimentation. All right, so before I actually experiment, before I actually go out in the world and test and see what the experimental probability is of a certain event happening given a certain sample space, I'm going to be just thinking of it in purely abstract terms, right? I'm just going to be thinking of it, okay, there's a die, I have 6 sides, 1 through 6. What's the probability of my rolling a 2? That would be theoretical probability. Right. So you can express that, or we'll express that in the terms of this. So P event, this is how you write probabilities. So the probability of some event, big P standing for probability, is the same as the number of favorable outcomes divided by the number of possible outcomes. Thank you. Okay. Liberty and Cameron, you both here? You've been summoned. Cameron Martin. Some of my work as well. Okay. So let's say we're considering a 6-sided die, and we want to know what the probability of rolling a 2 is. So P rolling 2. All right, so the number of favorable outcomes, favorable as in desired. So our desired outcome here is 2. So we would have the number of favorable outcomes. What's our number of favorable outcomes here? How many outcomes do we want? Yeah, just one outcome, right? 2. We just want one number out of those 6. And what's our sample space? What's the number of possible outcomes? Right, exactly, because there are 6 sides on the die, 6 numbers. So our probability is 1 over 6. Now, usually you'll express probability in terms of a fraction. So it would be 1 over 6. But you might also see it expressed as a decimal. So if you hello, phone. S4. Sure. Abdul? Yeah. If you can go to attendance. All right, he's on his way. Bye. All right, what's the probability of my getting interrupted again? That's the question. Okay. So you can express it as a decimal 0.1667, or you could express it as a percent. Well, how do you convert this to a percent? You move the decimal over twice here. Boom, boom. 16.67%. Okay, so it can be expressed any of these ways. You'll mostly be doing it in terms of a fraction, though it might give you a problem where it's like there's a 15% chance of rain or something like that, in which case you want to convert it to a decimal, move the decimal over twice to the left, you have it in your decimal form. Right. Now, notice that our percent, or not our percent, but our probability is 1 over 6, is less than 1. Your probability is always going to be between 0 and 1, including 0 and 1. So if the probability is 0, it means that there's a 0% chance of something happening. So for instance, my probability equals 0 when I consider the chance of rolling a 7 on a 6-sided dice. Right, because, okay, so I want to roll a 7, that's my desired outcome. How many favorable outcomes are there on a 6-sided die that are 7, 0, so it's 0 over 6 possibilities, this could be 0. Likewise, my probability is going to be 1, or certain, or 100%, when rolling any number between 1 and 6. on a 6-sided dice. Why? Well, that's because I have 6 desired outcomes, 1, 2, 3, 4, 5, or 6, and there are 6 possibilities. So I'll get one of those. Or there'll be a 100% chance that I'll receive one of those. Okay, and then as you specify conditions, right, as you narrow your favorable outcomes, you want all the even numbers, the odd numbers, you want 2 and 4, or whatever combination, then you'll be reducing that to somewhere between 0 and 1. So if you ever have a problem and you're working through it and you end up coming out the other side with something like the probability of this is 15 over 4, then you definitely know something's gone wrong. All right. So if it's over 1 in any way when you're calculating probability, you know you've done something wrong in the problem. So that's a good indicator to go back and check. Okay. So that's theoretical probability. Let's go to experimental probability. And experimental probability measures the likelihood that an event will occur based on the actual results of an experiment. Okay, so unlike theoretical probability, here we're actually looking at the likelihood of something happening based on doing actual experiments, right? So sometimes you'll see this in terms of sports. So you'll say like, oh, a batter has had 67 at-bats and has hit the ball 35 times out of those 67. That's ridiculously good. But so the batter has this particular batting average. Now, over the course of the season, if he has 100 at-bats, how many balls is he likely to hit? What's the probability of that? So that would be something like experimental probability. And we represent that. It's very similar to theoretical probability. You just have to think of the numerator as the number of times a favorable outcome occurs. So it's the number of times the batter actually hits the ball, let's say, divided by the number of times the experiment is done. So the number of times that he hits the ball and succeeds over the number of times he's actually at bat. Yes? Please. You're good. Okay, so that's experimental probability. So let's take an example. Say we have a basketball player. Made 23s. Of his last 34 shots. Past the 3-point line. All right, so this player makes 23s of his last 34 shots past the 3-point line. That's our background information. And we're wondering first, what is the probability the player makes a 3-pointer? All right, so just what's the probability? So how would we set this up? Well, probability of a three-pointer, let's say. And our formula here is the number of times a favorable outcome occurs. Sorry, should add outcome up there. What's our favorable outcome here? Anybody know? The favorable outcome is just that the basketball player makes a three-pointer, right? That's what we're interested in. What's the probability of his making a three-pointer? So we're wondering, okay, what's the probability of making a three-pointer? That's our desired outcome. And we know that, okay, he's made 20 threes of his last 34 shots. So the times the favorable outcome occurs, that's just 20. And that's over the number of times the experiment is done. Well, the experiment in this case is kind of a scientific word for basketball in any event, but it's just the fact that he tries a shot past the three-point line, right? That's the experiment that's done, so to speak. And how many times was that experiment done? Well, 34. So the probability of making a three-pointer for him, based upon the experimental data, that is the number of times he succeeds, the number of times the favorable outcome occurs, over the number of the times that the event's tried, or he tries to make it, that's just 20 over 34. And you can reduce that to 10 over 17. Make sure to reduce if you can. Sometimes you can't, and if you leave it in the larger form, I think you'll be fine. But it's always good to reduce. Yes.
Does everyone ask this for a decimal or percentage?
I have to check on that, but it might. If it asks for a decimal or percentage, you'll probably, unless it's something like a half or a three-quarters, you'll probably be using the calculator to do that. So. Okay. Now, let's see, I'll just go to the next page. Boom. There it is. Okay, so B, if the player attempts 100 shots in a season, how many threes is he likely to make? Okay, well, based on the data in part A of the question before, we figured out that the probability of his making a three is 20 over 34. Because he had 20 shots made over 34 shot attempts. But now they're asking us, if he attempts 100 shots, what's the amount that he'll probably make? How many will he probably make? So that means that, okay, there's 100 shot attempts, so our number of tries, basically, our number of attempts goes on the bottom. Those are the number of times the quote-unquote experiment is tried. So the experiment in this case is just shooting the ball past the three-point line. So 100 tries, how many is he expected to make? So we'll put X on the top because we don't know yet what that number is going to be. Yep, cross multiply. So I'm just going to put the X on the left. So 34X equals 2,000. Thanks. Then you divide 34 over. You plug that into your calculator. And you get that X is approximately, if you're rounding to the whole number, so you're rounding to the nearest shot, it's approximately 59. So that means that if the player attempts 100 shots in a season, a good guess is that he's going to make 59 of those 100 shots. Yep. Because you're looking for, okay, you have, every time he makes 34 shots, he makes 20. Every time he attempts 34 shots, he makes 20. What's up? Yeah, exactly. Yeah, so this is the number of shot attempts. This is the number of shot attempts. This is the number of shots made. X is the number of shots made. We don't know that yet, so we're solving for X. And this makes a lot of sense because 20 over 34, if you convert that to a decimal, it's going to be 0.59. if you convert that to a percent, well, actually, this is just the same thing. 50.59 is just the same as 59 out of 100. And that matches up with this. So you see that, this percentage, just to say, out of every 34 shots, outshot attempts, he's going to make 20, or he made 20. So his percentage of success is about 59%. So then if you have 100 shot attempts, then it's just going to be 59. So as you raise the number of attempts, everything's going to basically the probability is going to remain the same, while the number of actual shots made is going to change. So, all right, let's do an example with theoretical probability, and we'll use dice again. What is the probability of each sum when rolling two six-sided dice? Let's go 6. All right, our three cases are sums that add up to 10. Let's go with 4, excuse me, and 7. Okay, so two six-sided dice. We're going to roll. We're going to try to figure out, okay, what's the percentage of those when I roll those two dice of the numbers on there adding up to 10, 4, and 7. Okay, if you can't figure this out off the top of your head, one of the ways to do this is to create a nice little nifty chart. So it'll require a bit of artwork on our part. Okay, so we have a nifty little chart. And we'll say that this is dice 1, let's say, and that's dice 2. Now this represents our total sample space. So remember, the sample space is all of the possible outcomes that we can have. And when we roll dice 1, we're going to get one number between 1 and 6. When we roll dice 2, we're going to get one number between 1 and 6. And so in total, we have 36 possibilities of, or 36 potential sums that are going to occur. So that's represented by each little box, right? So that means that for A, B, and C, we're going to have some number over 36. Now, what's our probability of rolling 10? Well, we just think of, okay, what are all the ways in which these numbers can roll to add up? Oh my goodness. Thank you. What are all the ways these dice can add up to 10? Well, if I rolled a 5 on dice 1, I can roll a 5 on dice 2. If I rolled a 6 on dice 1, I can roll a 4 on dice 2. So 2 out of 36 ways of adding up to 10. Okay, but we have to consider another possibility. So it could be the case that on my roll with dice 1, I roll a 6, and dice 2, I roll a 4. But it can also work the other way. So I could roll with dice 1 a 4, in which case I have to roll with dice 2 a 6. And these, so I can mark that box. And these two things are two separate, sorry, let me move that down. These two things here are two separate probabilities. These are two separate outcomes. One outcome is that I have 6 on dice 1 and 4 on dice 2. The other is I have 4 on dice 1 and 6 on dice 2. So make sure that you take that into account. Okay, so in total, I can see that 3 outcomes out of the total 36 add up to 10. So I'm going to put 3 over 36, which I can then just reduce to 1 over 12. And let's say I want things to add up to 4. Okay, well obviously I can choose roll 1 on dice 1, roll 2 on dice 2, 2 and 2, roll 1 on dice 1, 3 on dice 2, 1 and 3. But I could also roll 1 on dice 1 and, 1 on dice 2 and a 3 on dice 1. Oh, actually, I'm sorry. A should be 4 out of 36. That's my fault. So, backing up a little bit, when you're considering 10 here, and the different ways to add up to 10, if we're taking into account that order matters, so the order in which they add up to 10 matters. So if I roll dice 1 and I get a 6, I roll dice 2 and get a 4, that's one outcome. Another outcome is rolling dice 1 to get a 4 and dice 2 to get a 6. It's also the case that if I roll dice 1 and get a 5, roll dice 2 and get a 5. Actually, does that matter in order? No, it doesn't. Never mind. We're good. I'm thinking too hard. Sorry. I'm anticipating another kind of problem. Okay, so then for 4 as well, we're going to have 3 possibilities out of 36. And that's just going to be 1 out of 12. Okay, and then finally, we're considering things that add up to 7. So the interesting thing here, maybe you've noticed a pattern already on this chart, but the interesting thing here is that if we roll 6 or 1 on dice 1, roll 6 on dice 2, that adds up to 7. Roll 2 dice 1, 5 dice 2. And it's just going to keep going 3 and 4, 4 and 3, 5 and 2, 6 and 1. So we'll have 6 out of 36 possibilities, or 1/6. So all of the sums, when you roll 2 6-sided die, are actually, if you chart them like this, functioning just in diagonals across, which is kind of a fun pattern that happens. So, fun fact about dice. But this also allows you to easily calculate when you're playing something like Risk, let's say, and you're rolling 2 dice at the same time. This would allow you to actually make some reasonable moves based upon, like, okay, how much should I bet on this particular move if I'm rolling 2 dice? Because I know the probability, I need to roll higher than a 7, and I know that probability, let's say. So there's some practical aspects to that. This also works in counting cards, but I'm not going to teach you how to do that because that's naughty. Right, so now that we've done that, there's one last thing. It's called the complement of an event. There we go. Complement with an E, not with an I. We're not complimenting people. The complement event is all possible outcomes in a sample space not part of the event. Okay, so the complement event is all the possible outcomes in a sample space not part of the event. Sorry, event there is kind of a little messy. So that means, like, For instance, when we were considering the probability of these particular sums, if I want to know the complement of C, rolling 2 die in such a way that they add up to 7, I'm going to be taking out this diagonal row here. I'm going to be considering the complement of the event as every other box aside from the ones that we want, aside from these ones that add up to 7. So the complement is just that whatever's left over from the original probability. So in that sense, my probability of rolling a 3, or rolling less than 3, sorry, on a 6-sided die is 2 over 6, or just 1/3. And my probability of not rolling 3, or less than 3, so rolling 3 or higher, is 4 out of 6, or 2/3. So the first one here, rolling less than 3, is an event. Probably not rolling less than 3 is the complement of that event. And if you add these up together, you just get 3 out of 3, or you get 1. So the probability of some event plus the probability of some non-event, or the complement of that, it's just going to equal 1. Because if I'm saying, look, the probability of my rolling less than 3 is 1/3, the probability of my not rolling less than 3 or rolling 3 or higher is 2/3. What I'm saying is, if I consider those together, I'm saying the probability of my rolling any number between 1 and 6, which is just 1. I'll definitely get a number between 1 and 6. One way to find the complement is to take then 1, so certainty, and subtract the probability of the event from that. So if I wanted to figure out the probability of not rolling less than 3, I would take 1, and I would subtract the probability of rolling less than 3 from 1, which would just be 2/3. Okay, so you'll be asked to find the complement sometimes, and the information you'll be given is only enough to figure out the probability of an event, so then you'll have to subtract the probability of that event from 1, and you'll get your complement.